Okay, welcome everybody. Can you hear me? Okay. Thank you very much, Mark Garneau, for inviting me to do this keynote, and to the BCAMT, and especially to you, all of you, for coming. SFU cohort, extra credits for showing up this morning. I just want to say, I know there's people on the sides, and actually what I have to say is probably less interesting than what I have to show. So if there's a way that you can move a little bit into the middle, right there or right there, it'll be much more interesting for you than if you can't see the screen. So my talk today is called Moving Mathematics. And the word moving I mean to use in two different ways. There's the one way of moving, which is about motion, things moving in time and space, like the BCAMT logo. Thanks to Mike Pruner for that. And also I mean moving in the more affective sense. So what is it that engages us, our emotions? What is it that makes us love mathematics or get really into mathematics? So my talk today is about moving mathematics, and for two reasons. Because moving mathematics engages learners more, and moving mathematics embodies mathematics better. So I'm going to try and show you different examples of this and why I think that the moving part works on both of those sort of cognitive and affective dimensions. Okay, so why is motion relevant in mathematics? It certainly wasn't a theme in any of the classes that you took at university when you were studying mathematics, or probably before then. So when we look at the word motion, we have one hint as to why it might be relevant. And that is, if you look at the word emotion, it contains motion. So that probably means that emotion and motion are really strongly related. And they actually are. We are biologically predisposed to be very interested in things that move as hunters and gatherers. We attend to them. And what more do we want from our students than that they actually pay attention to what the mathematics is doing? So there's the attending to, but also things that move invite us to tell stories about them. And there's nothing more important in trying to understand something, to make sense of something, than to be able to tell a story about it. And we tell stories about things that change over time and in space. That's how we are as human beings. Motion is also relevant because of connections. So I know that we often try to connect that abstract mathematics to the real world for our students, and we find things that move, like the proverbial two trains in the distance that are going to intersect at some point or meet at some point, or balloons that are moving, or whatever. But we can also make mathematics itself move. And today, that's what I'm going to focus on. What does it mean to make mathematical concepts move? And how does that connect to students? It connects because, as human beings, they move too. That's a fundamental experience that they have in life. They move. Let's connect to who they are as human beings. And the last reason is because of variation. Mathematics is fundamentally about variation, about things that move. You know this in calculus. Calculus is the mathematics of change. We also know this in algebra, because you use that word called variable all the time, right? Variation, that's something that's changing too, so are parameters. In geometry, it's all about variation too. All definitions that we have, all theorems that we have, are about things that are not changing despite everything else changing. So if we take an example of the sum of the angles of the triangle, what's interesting about the sum of the angles of the triangle is that the triangle can be any triangle you want. It moves around, it varies. It wouldn't be an interesting theorem if it was just about one triangle. It's the fact that across all of that variation that the sum of the angles stays the same. That's the mathematical part. So variation is in all of the subject areas, all of the different strands. Okay, do you recognize this? Descartes, famous saying, "I think, therefore I am." He's the one who gave us the Cartesian coordinate systems. Those are the Cartesian coordinate systems that made everything static on our graphs. And you know, he was a very important mathematician, but also a philosopher. And what he gave us is the idea that we can separate who we are in our body from how we think. The abstract is different from the body. And when he said, "I think, therefore I am," he was basically saying, what I know, how I understand, has nothing to do with how I move and how I feel things in the world. Well, luckily, 500 years later, people are realizing that he was actually very wrong. And what philosophers, cognitive scientists, linguists, neuroscientists, educators, what everybody is saying is that what Descartes should have said is this: I move, therefore I am. That's what makes us human, is the way that we move through the world and figure out how to grasp for things, how to eat, how to get to places, all of those important things that we do, and that actually we can make some continuity between that and mathematics. Okay, so motion is highly related to technologies, and we can think of one of the technologies that we've had in math education for a long time in mathematics is the paper and pencil. And the paper and pencil is an excellent technology for things that remain static, right? After you draw something on it, it's there and it's not going to move, it's not going to change. So that technology is not so great often for helping us think about mathematics in motion, which is why sometimes it's hard for us to figure out how to make mathematics mobile. And one of the things that digital technologies have done, you can think of your VCR. A long time ago, you were able to press play, pause, go backwards, fast forward. We can play with time. We can play things over and over again. We can make things go continuously in time. And that's what technology gives us, digital technologies, is this ability to work with time so that we can put things in motion. So a lot of my examples today are going to be based on using digital technologies. I have a URL up here that is connected to a file, a Sketchpad file that I'm using. So if you have an iPad, you can download this file and have access to all of the sketches that I'll be using now and when you get back into your classrooms. A lot of the sketches that I'm going to be using, they don't have to be done in Sketchpad. They can be done in other DGEs. They can be done in Desmos. You can find similar things on applets on the internet. I'm using Sketchpad because I can fit it all into this one file without going back and forth. And I'm pretty good at using Sketchpad, so it'll go better that way. Okay, so what I'm going to do is go through several examples of what it might mean to make mathematics move in a way that covers, I hope, lots of different places along the K-12 curriculum and lots of different topic areas that you teach in that curriculum. And I'd like to just thank a lot of the teachers here who have invited me into their classrooms to try some of these things out, and students who have told me whether that was a good idea or a bad idea, and other people who have been really helpful in developing sketches. Okay. Let's look at the first example, the triangle. So if you walk into most primary schools, there's a poster on the wall. It's not necessarily this poster, but it's some poster that has shapes on it. And usually the triangle looks like this one here. That is not a triangle in motion. That is a static triangle that is not giving us much of a sense of what a triangle can be. And it can't. It's on a poster. It can't move. But what happens is that children develop a sense that that shape, that specific shape, is what a triangle is. That's why they have trouble when they get to middle school and they can't imagine that the altitude of the triangle falls outside of the triangle, because they've been thinking of triangle in this way for a really, really long time. They get a long dose of this before they get to junior high school. So what I want to show you is a quick video of some students. They're kindergarten students. This is the first time they were working with dynamic geometry. And they're the students, I had asked them before drawing this triangle what a triangle was, and many of them said, it's this, or I am a triangle. And I asked them how we might make a triangle, and they said, make 3 sides and connect them. So that sounds really good. I was like, oh, my work is almost done. They know what a triangle is. So I want you to watch what happens after we do that. That is not the kindergarten student. Either is that one, either is that one. I apologize in advance for the quality of the video. We're connected, so we'll make them connected like this. Is this a triangle?
Upside down. Do it right side up.
What's wrong with this one?
It's upside down.
Why?
It's supposed to be.
But you didn't tell me that a triangle was 3 connected points that was right side up. You just said it was 3 connected points.
You can try to get the paper.
I will make it.
Like this.
You don't like it.
I can see it like.
Oh, you're going to turn around.
Right side up one. I do this.
So remember our extra special tool. We're going to use it to move the triangle around. Okay, I want you to watch what I'm doing now, because I'm going to ask you to tell me what you see when I do this. What do you see?
That's actually a triangle.
It's a what triangle?
It's actually a triangle.
Actually a
It
triangle.
is.
Why is it a triangle?
You can stretch it out.
And that's what makes it a triangle?
Yeah.
Oh.
You're gonna make.
Just say Asia, what do you say? What do you want to do?
Every triangle could be this different shape, but it just has 3 corners.
Okay, so obviously what I did was drag these vertices around. And I want to look at what Deja had to say at the end, because it captures, I think, a lot about what is mathematically relevant. It was obviously all of these kids were very interested, right? They were watching the triangle go. But mathematically, what is relevant about what she said? Every triangle could be a different shape, but it just has 3 corners. So she is talking about every triangle. That is generalization. She's not talking about just one triangle. She's talking about the idea that there could be lots of triangles. And not just that, but there's variation in that the triangles could be different. So she's imagining different types of triangles and not just that isosceles one that has a base horizontal to the bottom of the screen. And finally, she is talking about invariance. It just has 3 corners. That is the first step towards working to a definition. She's saying what has to be there in order for this thing to be a triangle. And why is that so powerful? Because she only watched that triangle move for a very little bit. But when we watch things move, transform continuously like that, it's much easier to see what is changing and what is staying the same. It's very different. You can give lots of different discrete examples, but it's much harder to see the invariances with discrete examples. So you could also do this on a geoboard by moving some of the points around and trying to get that continuity there. Different places to do it. What's important is to be going for that generalization, that variation, and then looking for the invariance. Okay, so even when we're working with digital technologies, that doesn't mean the paper goes away, but we can imagine trying to make the paper more alive as well. So whenever I'm working with children in these kinds of settings, I always ask them to draw what it is that they've done. So this is one child who was working with dragging a triangle on an iPad, so you can see the finger is there along with the triangle, which I quite like. But what's important is that there are different types of triangles there. The student is imagining those different types. Here, this is for the theme of the conference. I didn't tell the child, but you see all the hearts there. I love triangles. But also you can see the arrows, which are sort of showing the change over time of these triangles. So the child is using arrows now to try and capture the time dimension. And in this one, you see the change not just in pulling the vertices in this bottom triangle right here, but in the other triangles, the arrows are going like that, and the arrows are going like that. So even though it's static with the arrows, you can see a lot of motion that the child is trying to communicate about the triangles. So we don't have to leave paper and pencil behind, but we can reanimate paper and pencil as we move back and forth between digital and non-digital media. Okay, don't worry, I'm not going to talk about geometry the whole time. Let's look at a different example. This is an example involving addition and subtraction. So from cognitive scientists, we know that there are some basic metaphors that we use to make sense of mathematical ideas. So the idea of addition, you can think of it as gathering things together, right? You have a bunch of candies here, a bunch of candies here, you gather them together, and that's basically your idea of addition. Take some away, and you get subtraction. So those are things that kids do very early on in life, and they gives them some fundamental understandings of addition and subtraction. But as we know, that particular metaphor works for a while, but it's very bad for thinking about negative numbers or rational numbers. So another metaphor that we also use is called motion along a line. So that's the idea that when we move forward, we're adding. The further we go, the more we're adding. If we move backwards, then we're taking away. And we also experience that in everyday life as we're walking along a road or walking along a path or getting to our bedrooms. So it's a very powerful metaphor to use, and why I like it is because it fundamentally involves motion. So let's just see how this one works. I'm going to jump by 2, and when I press jump, I go by 2. So we'll do that a few times. What's important here isn't really the arcs. I know we have a lot of representations of those sort of arcs in our textbooks. What's important is actually the motion, is actually seeing that rabbit go forward. This is +2, +2, +2. And then if we want to go backwards, so building up our ideas of subtraction, -1, -1, we actually are going backwards and thinking of that as a subtraction. So we could ask questions, well, 2 and 1 is a little bit boring, so let's change to 2 and 7. Or 7 and -2. So in a situation like this, so going by 7 is a lot more exciting than going by 2. You get to go up, but we can imagine asking some interesting questions, like if I have 7 and -2, will I be able to get to 13? If you need to multitask during this talk, you can work on that problem and come up with some more interesting ones of your own. So I'd like to show you just some pictures of children working on this. And what's important is that as they're watching, as they're making that rabbit go, they're following the rabbit with their hands like this. So they're developing, internalizing for themselves what that really feels like to add. And why is that important? Because when they get asked to do questions around addition and subtraction later, even maybe on a test, they have a way to go back to. They have an image and a feeling to go back to help them do those operations. So you might not be able to see them, but on the math journals that they have, the kids are writing these incredibly long equations like 7 + 7 + 7 + 7 -2 -2 + 7 equals something. I didn't keep track. Here we can see more clearly some of those equations. So they're connecting. Again, it doesn't mean that just because we're going to use motion that we let go of all of our other technologies. We still want to connect that motion to the operations. So connecting this to the symbol plus is really the key. Okay, let's keep with the number line idea and look at multiplication. So multiplication is another topic that comes across as being very static. There are all of those multiplication tables and all of those facts that we remember, or not. But let's think about multiplying as an operation. And for those of you who teach a lot of functions, we can even think about multiplication as more of some kind of function, that we sort of don't care what the result is. We just want to understand how it works as a function. So in this sketch, as I move, I have AB, which are the multiplier and the multiplicand, something, right? The two numbers. And A times B right here. So I can move A and B and watch what happens to A times B. So as I move B to the right, I see that A times B gets bigger and bigger and bigger. And that it will always just keep getting bigger and bigger and bigger. That's a really important thing about multiplication. The more I multiply it by, the bigger it'll get. It does not anything special about B. The same thing will happen with A. If I multiply by A, also the product will get bigger and bigger. Then I can notice some really interesting things. If I put A at 1, B and A times B are like tight friends. They're together now. And that's a really important thing, multiplying by 1. It's really more interesting to see it that way, to say anything times 1, is that anything? Because now what we can do is that we move B and we can see they always get stuck together. They're like married. Really interesting behavior that it has there. If we move A to 0, we get another really interesting behavior. This is like the zeroification is what some students call it. So now everything is stuck at 0. And no matter how I move B, that'll be stuck at 0. I didn't get it exactly on 0 because I'm a little nervous, but you can imagine what it would look like. Okay, let's just look through one example. Actually, another important thing, I know you encounter this a lot with kids that come to think of multiplication as always making things bigger, that when you multiply two numbers, they always get bigger. But what I've done here is change the axis so I get more access to stuff between 0 and 1. So here I can see that if I'm going to multiply B by something that's between 0 and 1, actually my A times B is getting smaller. So something really interesting is happening between 0 and 1, and between 0 and -1, that's very different than what's happening outside of that. Okay, so let's leave A there for a second, and let's just look at overall behaviors. So A is fixed, and I'm going to move B. So as we said before, if we move B to the right, B is getting bigger, then the product is getting bigger. As I move B to the left, B is getting smaller, and the product is getting smaller. And it just keeps getting smaller when it goes into the negative. So it's just staying continuous. It's behaving in the same way that we expect. It doesn't like hop around at 0 and go in the other way, right? It just keeps going as it did when it was in the positive. Okay, so now let's leave B as a negative number. So here we have A as a positive number and B as a negative number. And we can make A bigger, in which case A times B is going to get smaller and smaller and smaller. And now let's make A smaller, in which case B is getting bigger and bigger and bigger. And again, by continuity, when it gets to 0, it doesn't hop around in the other direction. It keeps getting bigger. So that's an argument through continuity of why a negative times a negative is a positive. We just have to look at the behavior over time instead of remembering negative times a negative is a positive. So I want to show you a short video of a university student who was at SFU. We asked her first, in the first part, we asked her, I think, what -4 times -7 is. You'll see what she says. And then we spent half an hour doing different tasks using that multiplication sketch. And later on, a month later, asked her again about the product of two negative numbers. If we wanted to do something like -4 times -7.
Oh yeah. -4 times -7. That one works because well, you take your first number and you go to the left to the -3, -3, and then the other one would go to -5, but then your answer, your product, would be a positive 15, right? Mm-hmm.
Okay, so for me what's important about that is that when we first ask her, she doesn't know where to go to get an answer. I don't know. She's laughing, she's nervous about it. And is everything okay? Okay. But after, she knows in her hands how it works. She shows us through her gestures. She can see that happening. She has a place to go to try to reason about what's going on. So when we ask kids math questions, sometimes what really gets in the way isn't that they don't know, but they get really nervous. If you're really nervous, you can't think. You need to have other resources to call on, other images, other ways of moving your body that can help you make sense of those kinds of questions. Okay, let's move to statistics. Just one brief example here. This is a sketch where we just have 5 data points on this one, but it's enough to illustrate the point. So the orange vertical bar there is a median line. So if you just look at it like this, it's very boring, right? There's nothing interesting that's happening. Now let's try moving some of these data points around. So imagine that the data point wasn't at 9 anymore, but that the data point was going to be more positive. What's going to happen to the median line? Pardon me? Nothing. Nothing's going to happen to me. What would I have to do in order to get that median line to move? I'd have to move that actual point. So let's check that out. When I move that data point, nothing happens. Is there any way I can move this data point to get something to happen? So I can move it across here, and there's going to be a certain point where that median is going to now be associated with that data point, because it's now in the middle, and now nothing is going to move either. So here we're seeing the behavior of median, and what changes about the median as we move these different data points. Finding the median, saying that the median is in the middle, is not statistics. That's arithmetic or a little geometry. What's important is figuring out, if that's the median, what kind of set of data points might I have? What do I know about my data points if I know that that value 4.7 is the median? Well, what I know is that I have a value of 4.7, but I have no idea. I could have my data points being super wide apart, like this, maybe all bunched here. And that's a very different kind of data distribution as if I have them all bunched over here, but both of those sets of data have that number 4.7 as the median. Okay, let's look at the mean. The mean is sort of more interesting because the mean, whenever I move something, the mean is going to move as well. So the mean is much more sensitive to the value of the data points because it moves all the time, unlike the median. So I can make it move to the right by making my data points bigger, and make it move to the left by making my data points bigger. It's really exciting when I can make the median and the mean equal to each other. Okay, here we go. So did you ever wonder that? What kind of data set will have the same median and mean? And now what would I have to change in order to keep the mean and the median the same? What is the range of data sets that's going to have the mean and median going to be the same? What could vary? And here we're coming back to the idea of variation. Statistics is about variation. It's about looking at what could change in your data set to affect those values of mean and median. Okay, let's look at an example of symmetry. Just a first point, when we work with symmetry, we're actually working with a transformation of reflection. So symmetry is a particular, there can be different kinds of symmetries, of course, rotational, reflectional symmetry, but you get symmetry by doing reflections. So that's one way. Symmetry is a noun, but reflecting is a verb. So if we focus on that verb part, we can get the motion back in because we can look at what does it mean to get something that's symmetric. So here's a ladybug. And let's look at how really symmetric it is. So I'm going to assume that the line of symmetry is about there. And try to, sorry, that was terrible. trace over my bug here. Okay, so if my bug is symmetric, then if I take that left side and do the reflection onto the right side, then it should fall onto the right part of my ladybug. So I'm going to say that's going to be our line of reflection, and let's reflect that ladybug. Okay, it's not really a symmetric ladybug, but it's pretty close. Actually, nothing in the real world is really symmetric. It's always a bit of a fudge factor. But since we're doing math, let's just forget about the real ladybug and look at how reflection happens. So in reflection, it's not enough to say, oh, it's symmetric. What we're really after is what are the properties of symmetry? How do symmetric things behave? So if the ladybug sees a little, I don't know, what is a predator of a ladybug? Like a frog or something? A bird, okay. A bird comes by. Wah! It gets all really, you know, this is what's interesting about a ladybug. Not that it's symmetric, but if one thing moves, the other thing moves as well. And it moves in a very particular way. It doesn't just randomly have one leg go like this and one leg go like this. So same thing with the different parts of the ladybug. So, you know, just playing with this is fun, and definitely there should be time for that. But we can also start thinking about mathematically what's going on. So if I start being a little bit more careful, I see that if I move one leg away from the line of reflection, the other leg moves away as well. If I move one leg along the line of reflection, the other one moves along as well. And once you're starting to think about that, you're starting to get a lot of ideas about how reflection really works and what the geometrically interesting ideas around reflection. Again, it's looking at invariance. It's because we can see it move that we attend to some of these properties. And then we can also look like, oh, well, it looks like there's sort of the same amount of, you know, your students might say the same amount of space away. Maybe they'll come up and notice that this is sort of the same as that. And maybe at some point it's worth calling that distance. But again, those are properties that are very obvious once you start moving them around because you can attend to them. So because we have our line of reflection and this is all dynamic, we can also like do a little dissection. So if we move the line of reflection, then we expect the two sides to behave in a certain way as well. I started with a diagonal line of reflection because we spend too much time doing this one, which gets us into a lot of trouble later on. But if we really want to get that one back again, there's no problem. We can look at the vertical line of reflection and make up new animals. So here's my insect. Okay, so with some grade 2-3 children, we were working with symmetry using this symmetry machine. When they drag the red point, the blue point behaves as it should under symmetry. Because of the theme of the conference, I feel like I should do this. Okay, so that looks like fun, and you might be wondering, well, that looks like too much fun. It can't be really math. But I want to show you some kids who were working on trying to get make certain shapes. This is on an interactive whiteboard using that sketch. So that we have a diagonal line of symmetry, and they made hearts and all sorts of things. And one child said, oh, I wonder if we can make a square. So you might want to think about how you would actually do that yourself. And let's see what the boy does, how he manages.
Really breathe.
Nicely done. But you don't have it. Okay, good. Very nice. Well done. That's a really nice square. Okay, here's a big challenge for you. Do you see how this square is a bit tilted?
Yeah.
Do you think it's possible to make a square that's not tilted?
Yeah. Townhouse. Better, you
Oh yeah, you did make it.
Well, that. What was she? I didn't like it that I wanted to. It doesn't matter. Yeah, he's doing good.
Very nice. So So even the kids are surprised that he's doing it. You hear that one. But they were very attentive again. I mean, it's very interesting to watch things move and to watch to see if your friend can make a square as well. But there's a lot of geometrical thinking and trying to think about what is the half shape and how do I have to make it in order to get my full square. Okay. Let's go to area. So I actually brought this stack of books right here, but I need them to prop up my computer. So what this stack of books is doing is, I'm going to sort of model the stack of books. So there's my stack of books. Okay, it's a bit off a little bit, so it actually looks more like that. Okay, so if you look at that, you might disregard the fact that they're books and see a rectangle there. And what we could do with that rectangle, so you're basically looking at this side, for those of you who can see me, a bunch of spines right here. We can think of that as the area of the rectangle. But imagine you took that stack of books and you just moved each book over a little bit. So you're going to take the books and do like this. You could do this with cards as well. So what that would look like is that each book would move a little bit over like that. And now what that looks like, or what it should start to look like, is a parallelogram. So now we're seeing that by moving that over, we're getting a shape that's a parallelogram, but its area hasn't changed because those spines, they haven't changed in size at all. They're just moving over a little bit. And actually, this is a way of thinking about area that is very close to our ideas of calculus. If we made these a little bit smaller, they would maybe start to look more like a parallelogram than when they're a little bit bigger. But basically, that idea that if we shear something, so we move all the slices over, that we don't change the area, is a way of thinking about area conservation in a way that we don't even have to think about formulas or numbers. We're just saying that area is the same as the area of a rectangle. Of course, I didn't have to move everything over. We only do that because we happen to be interested in parallelograms, but you could move every spine over in some arbitrary direction, and now you've got the area of a crazy dodecagon or something like that, many side. 3 minutes? Really? Okay. Okay, so if we don't look at the spines, here's an example of that. So the areas of all of those parallelograms are exactly the same. And we didn't have to use parallelograms. We could have used a triangle as well and gotten the same idea. So here I'm finding the area of the perimeter. Now I'm finding twice the perimeter. And we see that indeed, the perimeter is changing, but that area is not changing at all. Now, why would you want to know those kinds of things? Well, first of all, a lot of our ways of thinking about areas with kids is to think on the left about algebra, but the point of doing area isn't to do more algebra. The point of doing area is to think about measurement as a way of conserving measures. So here's a grade 8 student from Eulam's class who was showing different ways of thinking about shearing, either through dissection or through shearing. And what's nice when you have that is that you can solve problems like how to turn a hexagon into a triangle without using any formulas. You just shear the sides and go from a hexagon to a triangle, and then you're done. As long as you know the area of a triangle, you're done. Even more, we can solve the Pythagorean prove the Pythagorean theorem this way. We'll take those squares on the side, shear them, they become parallelograms, shear the two rectangles, they become parallelograms, and we've proved that those two shapes, A plus B is equal to C plus D. And just leave you with a nice visualization here. If you're ever wondering how the radius of the incenter of a triangle is related to its area and its perimeter, here it is. We're going to move those around, then we're going to shear them, and then we have a way of relating the area, the perimeter, and that radius of the incenter. Okay, Let me do one more quick example. So actually, I didn't get to the three pre-calc examples that I wanted to do. So if you come to my session that is happening next, I promise I'll do more high school stuff. I just want to close with this one example, which several of you know already, but it's appropriate for the theme of this conference. So I'm going to take a circle, and I put a radius in that circle, and I'm going to imagine that I'm trying to move B around the circle, and at the same time, I want to try to move A along the radius. So if those two motions are happening at the same time, what do you think is going to happen to A? What kind of path is A going to trace as that's happening? So I see lots of people doing this with their fingers. That's good. Okay, I don't have time to let you think about it too much. So what we're going to do is we're going to trace that. It's all Mark's fault. Okay. And maybe this is what you had in mind. So as that point B is moving around the circumference of the circle, point A is creating these leaf-like things or these petal-like things. It looks like it's going to create 3 of them. Oh no, a little more than 3, but not quite 4. We're math teachers. What number is that? Pi. Why is it creating pi number of petals? So think about what's happening. That point B is going once around the circumference. 1 petal is 2 radii. So we're basically asking how many 2 radii are there in 1 circumference. You all know by heart that formula. We're putting it into motion here because we're looking at the relationship between circumference and diameter. And that relation is the circumference is equal to pi times the diameter. So I should have exactly pi petals for 1 turn. Now I'm letting it turn a little bit more. And I don't have time, but if we let it turn quite a bit, in fact, if we let it turn 7 times, we're going to have exactly 22 petals. So that's a nice result. But what I'd like to do is to play a little bit with the speed. So now let's think about keeping that radius moving at the same speed. But now I'm going to make the circumference move quite a bit faster. So I'm going to take that circumference point, B, and ask it to move pi fast. Thank you very much.